But the process, it's really expensive and takes a long time because not only everything is made slowly, but then very slowly it has to cool down to room temperature before next treatment. In the first part of the wafer fabrication, we are going to talk mainly about silicon wafer fabrication and processing. So I would like to start with some interesting facts about silicon. And also, we will discuss why silicon is dominating the microelectronics industry. So one thing is that it is very easy to find silicon, a bit more difficult to purify it. So about 28% of Earth's crust is silicon, which makes it, after the oxygen, the second most abundant element on Earth, even though it's only the 8th in the universe. It has the atomic number of 14. We know that already. There is some data about the density, 2.33 grams per centimeter cubic, and melting point, it's over 1,400 degrees Celsius. So it never occurs in the free form. So we have to really make efforts to purify it. Typically, it exists as silicates, which is the silicon and oxide compound minerals. But there are also many other elements that will react and form materials together with silicon. Because of silicon being so easily reactive with other elements, that means that whenever we find it, it's in a compound form. And on the Earth, 90% of the Earth's crust is this silicon compounds, silicate minerals. So therefore, it's not surprising to see that we will find on average 1 gram of silicon in our bodies. In fact, considering how much silicon is on Earth, it's really not a lot at all. It was first purified in 1824 by Mr. Berzelius, a Swedish chemist, and it was in amorphous form. Actually, some years earlier, maybe 15 years earlier or something, it was still thought that it's not a semiconductor. People thought that it's a metal. And it was classified together with aluminum, zirconium, beryllium, and at the beginning the name given to the element was silicium, which still stayed in some languages. Now it's silicon. So this silicium at the end was supposed to indicate also like some other metals, like aluminum, that it's a metallic material. And only later it was possible to purify and actually show that it's a semiconductor. So only 30 years after the purification, it was prepared in crystalline form by French scientist Henri Deville. And since then, we only saw progress in the level of purification of silicon. Not to mistake silicon with silicone, which is a polymer. And let's have a look why silicon, why it needs to be crystal and why pure, because this is important in the fabrication. So we can see here a plot which shows resistivity as function of dopant concentration. And such accurate resistivity control, which in the logarithmic scale goes almost a straight line, we see some deviation from the trend at very high doping levels that actually the resistivity is not changing so rapidly anymore. But this we can achieve only when we add doping to crystal. So the crystalline polysilicon, in amorphous silicon, anyway, don't have the same properties, that we will not see the at very low temperatures. In the crystal silicon, we see that it's almost insulator. So we have also this dependency. But what we will see otherwise in polysilicon is that so polysilicon is multiple grains or lots of grains of monocrystal, and along the grains boundaries we will have the preferred path for the charge transport. So we cannot have for the undoped silicon, we cannot have such a high resistivity like for crystal silicon. And similar for amorphous, we also will not have that. And then if we try to add doping to polysilicon, then the dopant atoms, they will tend to be trapped also along the grain boundaries of these silicon crystals, but at the boundaries. So then we will not have such a steep control over the resistivity, because the dopants are not going inside the grains, but only at the boundaries. So it's only with the crystal that we can have the doping control property over a wide range of the doping concentrations. And also the same what we were already looking in terms of the temperature dependence. We will have only that for silicon, that when very low temperature, then we don't have charge carriers in case there is no doping. Then it is relatively cheap in fabrication. We can create wafers of silicon to quite large areas, in contrast to other semiconductors where the wafers will be much smaller. We have for free a dielectric, which easily forms. If we do nothing, actually it forms silicon dioxide. So if we want to make MOSFET transistor, it's relatively easy to make gate oxide. It's only the art of making it accurately controlled, because for a few nanometers gate, we really have to do it very slowly to know that all the transistors will have the same gate thickness with just small margin of uncertainty. The energy band gap, this is something that makes it really comfortable for using as consumer electronics, because the conductivity is, we have the charge carriers available at room temperature. At a too high temperature, there are too many charge carriers. So for automotive, for example, it's not automotive applications where we have very high temperatures, it's not suitable anymore. It is a strong material, although the wafer, we can easily break along the certain crystal orientations. And it has good properties for sensor applications. So in terms of sensors, for example, it's light sensitive. We can use it as light sensor. It's we can make, for example, capacitors which will be then sensitive to the pressure because of the small rearrangements of atoms, of atom distances. So we can sense capacitance. Also, what we can do is sense magnetic field because of the Hall effect in semiconductor. Or what else? Or temperature sensors, also based on silicon because of the temperature, known temperature characteristics of silicon devices. Now, here, this plot, we know already the silicon compared to gallium arsenide in terms of charge carrier concentration. So for room temperature, we prefer silicon. For higher temperature, gallium arsenide. And there are some big advantages of gallium arsenide. That's like an example semiconductor. And in fact, what triggered my thought is we have certain publications or articles in the newspapers telling still about benefits of silicon or gallium arsenide. So on one hand, we have why still silicon dominates the IC industry. On the other hand, 40 trends of emergence of gallium arsenide as substitution to silicon. So obviously, there is something to understand behind in order to create our own mind about that and to understand why still 90% of integrated circuits are based on silicon. So here is a small comparison. Gallium arsenide are definitely interesting for light-emitting diodes because of the direct bandgap type. Then the bandgap energy is larger. That's why the charge carrier concentration is lower at room temperature. Interesting features is maybe let's stop at some of them. Mobility of electrons and holes. So hole mobility is still quite poor in both cases, but the electron mobility is much, much higher than in case of silicon. And that's the, one of the main interests to use gallium arsenide materials. In terms of devices that can be formed, we can make P and N-channel transistor MOSFETs, but in case of gallium arsenide, we only make N-channel metal semiconductor field effect transistor. So the insulator between in the gate, it's not used in gallium arsenide because technologically it's more complicated. In terms of operating frequencies, thanks to the high electron mobility, we can achieve tens of gigahertz with gallium arsenide devices. But because we don't have N and P channel MOSFETs, and because we don't have oxide in the gate, we have only moderate power consumption in gallium arsenide. And finally, probably simply because gallium arsenide is not so widely used, we didn't see such progress in terms of scaling. So it's few hundreds of nanometers, the minimum gate length, whereas for silicon it's few nanometers. So we have here cross-section of silicon and gallium, it should be gallium arsenide here. And summarized the advantages and disadvantages of these devices. What I would like to show here is one of the big drawbacks is that we cannot make an inverter like we can see in the MOSFET operation of the transistor. We will have complementary P-channel, N-channel MOSFET forming inverter, which in the static condition doesn't consume power. Here, when the N-channel transistor, so N-channel MOSFET is on, we will have current, either because of the diode or the made of also N-channel transistor or because of the resistor. So the power consumption of these semiconductor devices will be much higher. So that's why we're going to talk about silicon, because most industry for integrated circuits uses silicon. We have really great improvements in scaling, in seeing more and more advanced devices, and I think that's where it's worth spending really more time. So what we will do is go through the wafer preparation, purification, crystal growth, slicing and polishing, and then go to wafer processing. We have where we stop and have also more discussion on that. But we have to remember there are also the steps of wafer sort, and in the back end, assembly and packaging, burn-in, and final test in order to make the product suitable to sell to customers, because that's what in the end is the point for producing them. So regarding the material purification, silicon originates from silicon dioxide or silicates, which are mainly found in the sand. In a chemical reaction with carbon, we obtain about 90% pure silicon and silicon dioxide as a byproduct. But then what we need to achieve is the 11/9 grade of purity of silicon. So there is still then much more work to purify it. So it will be 0.01 parts per billion of cleanliness level. That is the target. There are lots of impurities like boron, aluminum, iron. Later, of course, we might want to add, for example, boron as doping, but in a controlled and localized amounts. So, thanks to the fact that chlorine is highly reactive with those elements, there will be forming compounds which with iron, aluminum, boron, for example, which have then lower melting point than silicon and can be easily removed by distillation. In the end, what we have, so in this distillation also we're forming the new silicon compound, and from which the chlorine and hydrogen are removed by inverse reaction. And through this complex chemical process, we are achieving the very clean silicon. If there are still some impurities that we want to remove, hopefully there are such impurities which have the segregation coefficient lower than 1, which means that impurities prefer to stay in the melt than in the solid material. So the K segregation coefficient tells us what's the ratio of concentration of impurities in the solid to liquid. So when we have the silicon rod and we want to purify it, we simply melt some zone and with AC fields, and we sweep this field by pushing the molten zone further and further, which contains all the impurities, and this improves further cleanliness. Next thing is from the pure silicon, we want to form crystal. So the crystal is made by first melting the silicon, taking a seed crystal of known orientation, because as we pull it out of the melt, then all the new atoms that are attaching and crystallizing, they are going to follow the same pattern, the same structure of the crystal. So the known seed orientation has to be taken, and then there is the rotation, and at the same time pulling out with a speed of approximately 20 rotation per minute and 0.10 millimeter per minute pulling, so really slow. You can see that it will take really long time, so that to achieve approximately 2 meters rod, of which we cut wafers of less than 1 or approximately 1 millimeter thick, so we have plenty of wafers from that. But the process it's really expensive and takes a long time, because not only everything is made slowly, but then very slowly it has to cool down to room temperature before next treatment. And why that? Why it has to be slow? Is to avoid any mechanical pressure because of the temperature change. So the temperature gradient in the structure has to be as small as possible to avoid any mechanical damage of the structure. Just to remind, there are different crystal orientations, and depending how we start with which crystal orientation, once it will predetermine, once we cut the wafer, in which orientation the wafers will be. And there are some preferred orientations depending on what kind of devices we want to manufacture. And one of the importances for the wafer crystal orientation is the properties in the wafer processing. So some processes are directional. For example, if we want to remove material, remove silicon to maybe make some trenches filled with metal, then depending on the crystal orientation, the etching will be faster or slower. So also that means faster if we want to go fast, but slower means better control. Then diffusion constant, when we add localized doping, it will be different in different direction. And also for ion implantation, if we have a really badly chosen orientation of the crystal, then the ions can go in uncontrolled way, penetrate through the silicon and not stop just close to the surface where we want it to be. And the same for epitaxial growth, also it will depend on the orientation. And finally, we have also the surface quality. So depending how we cut the wafer into which direction, the number of dangling bonds, the atoms without the corresponding neighbor, will be different. And the smaller, the better, because we will have less traps as from the MOSFET transistor and channel point of view. You remember talking about the off-state current, for example, of noise. It will be lower the smaller number of the dangling bonds on the interface between silicon and the oxide. So for the different orientations of the wafer, there have to be marking to tell us if it's P-type, N-type, and which orientation. Nowadays, it's used with a kind of notch for marking the crystal orientation so that when the wafer is fed into the machine can recognize the orientation so that always it processes the transistors are facing always the same orientation, and then we have repeatable characteristics also because of the charge transport properties, as well as the technological properties for fabricating them. And so the 1-1-1 orientation is preferred for bipolar processes, for power electronics and radiation detectors, because the epitaxial deposition is preferable in this orientation, and these processes rely on that. And 1-0-0 is used for CMOS, MEMS, and solar cells, where the etching is important because it's faster in this direction. One important aspect is the wafer quality. So we have some impurities in the crystals, which partially the dislocations that are here can come from the thermal problems during cooling, and therefore we have to cool as slowly as possible. But there can be also missing atoms, which will be a vacancy, interstitial, which will be an atom that it's not located in the crystal structure. And also we can have impurity atom, which will be obviously also then different size than silicon atoms, causing some fluctuations in the crystal networks. This example shows just 2D, but in 3D we can expect that these dislocations will be more dramatic, as it can be not just punctual, but it can go over the whole dimension. And finally, one more topic about the wafer and fabrication in terms of growing the crystal, purifying and growing the crystal, and later processing, is that it has to take place in clean room. So clean room is the environment with temperature control and humidity control, so that also, for example, things like electrostatic discharge will not be too dramatic, and it will be in control so we don't damage the devices. Then we have air particle control, so that there is no additional impurity introduced in the environment. So for that purpose also we need to use selected material that it's not going to outgas too much and create additional particles in the air. And one of the facilities that also has to be provided is suspension of the clean room, so that any vibrations, for example, from motorway around, are not going to be propagating and interfere with the machines that try to work with nanometer precision. So that's why, because of these different facilities, we can talk about the onion-like structure, because we have all the different surrounding facilities, and in addition, we will have some environments which have even better controlled quality of the air, of the ambient, than outside. So, for example, some clean rooms, there will be restricted access of a human to the wafers, actually, and handling will be only done by machines, so that the cleanliness is even higher quality than when we have actually interference from human who are breathing, even though through the masks and clothing that go in and out of the clean room, even though we use air showers, but it's never so perfect as if actually we restrict from the human interference. And then also, because there are different production facilities, there will be different clean room classes that are classified according to the number of particles and their size. One more topic is the special containers that's exactly for the machine handling of the wafers in the clean room. So we have special containers that work in an interesting way, so that when the wafers are open in the clean environment and then closed and then taken into maybe contaminated environment, there is no connection of the surface of the container with the clean environment handled by the machines, such so-called Smith system. Yes, so the clean room topic is something that we have to be aware that the whole fabrication takes place in the clean room, and in the next topics we are going to see exactly the fabrication steps from the wafer to the device and actually the ready chip. So that's it for today. Thanks for coming, and see you hopefully next week.
You're the signal in my static hum, a perfect match we've overcome. Wires cross but we still run, sparks fly and circuits spun.